All right, then we can begin our lecture. So we last week we were going through the basics of set, as we know. Just basically rehashing, or other words, just revisiting what we have done before previously at pre-U level or secondary school level. So we stopped at proving identities. Am I clear? Can you hear me clearly?
Yes.
Yes,
Sir.
brother.
Yes, sir.
Yes.
All right then. So it's using just that it's very very quiet. Normally I can hear background sound and all. Though I've muted everyone, there are some who tend to somehow unmute themselves. So at this time it's very very quiet, eerily quiet. So I was just wondering whether you all can hear me. All right then. So for proving set identities, we know set identities are basically the equals to the one on the right hand side of the equation. So always think of it as like that, right? Something on the left hand side, whatever it appears, will definitely be exactly the same value as what you get on the right hand side. So when you have that idea, that concept in your head, in your mind, then it is very easy to later answer questions on set equality, right? Also for logical equivalences, because what we are doing is just basically saying what is on the left hand side has to be proved to be the same on the right hand side. So what we do first is never ever swap whatever you have, the variables, the constants, the numbers, from left hand side to the right hand side and vice versa. The biggest mistake you can make is to think that this is just like a simple mathematical equation, like any other normal mathematical equation, and then you just take a x value on the left and then you go push it to the right hand side. Don't ever do that. When you're proving for equality, like I said, for set as well as logic, always, if you're going to prove, you only prove on one side. That means you choose the left hand side and then you just go about proving step by step whatever you see only on the left hand side. So eventually what you get is something that is the same as on the right hand side. Now this is a tip for those who are a bit slow slow in doing the exercises and all that. Okay, you do enough exercises, you should be able to know how to attempt questions like this. So anyway, now the bulk of proving equality actually is focused in in logic theory. But because we have rearranged because we have rearranged the topics, I can't really go through the main method for this topic here. We will revisit that once we have completed the part in logical equivalences later on, right? But what we can do now is to see. So all these I have to skip, right? Because you notice that some of it are using what do you call that? Logical equivalences like symbols like this one. This is of course under set, but these are under logic. So you have to skip that for now. But what we can look at now is called a membership table. A membership table is actually similar to a truth table that we see in logic. For those who have done truth table before, a truth table is basically whether the value, the outcome is true or false. This is so relevant to computer science because we always see the binary numbers, digits, zeros and one. So representing a set membership table is in the same way, right? We look at using zeros and ones and the relationship between different types of what do you call it? Set relationships, right? Hmm. I wonder why it's not going full screen. Ah, what you can see. See my um, version of the slides, not full screen one. Get out of this. Ah, it give me a second. What they mean by subtitles? I don't have subtitles. Syndicate that button. Hang on. Going to like hopefully my laptop doesn't crash because of this. Yes. Hang on, my PowerPoint hanged. Thanks to WebEx as usual. Always does that. I'll be able to find a different alternative to WebEx. I'll just directly stream from my screen so you all can access. You can view the slides and I can actually annotate and write on it easily. WebEx just keeps crashing all my other applications. Oh, WebEx stopped working or the PowerPoint stopped working? Because I can see your message, but I can't see WebEx. All right, welcome back. If there was momentarily interruption to the WebEx online meeting, thanks to WebEx for being such a greedy application. I was having to close the PowerPoint and it just also decided to crash along with it. Yes, it is. Ask Unimas to cancel 100,000 over ringgit subscription and then we can use Zoom instead. Right, give me a second while I check on what made it crash. No, it didn't crash. Oh yeah, the PowerPoint itself, because it decided to show two different screens. I do not know why that was. Having to reset my whole computer, it has gone back to default settings anyway, so I should be expecting all this. No, this laptop doesn't need upgrade of RAM. There's enough RAM. It has an SSD hard disk as well. There's too many applications, so I have to reset this whole laptop and keep to the basics. I'll get a new one. All right. Hang on while I load. Attendance wise, let me see. So far, 328 and the 29. You only have to take attendance once, huh? You've already inputted earlier on. You don't have to do it twice. There's no option to say there's only a single answer. I don't know. Well, while waiting for PowerPoint to load, why sitting? It shouldn't take this long. I need to read. But anyway, what happened last week was I would usually shut down WebEx after my lectures because it just monitors the resources of the laptop constantly, and that happened before. So what happened last week was I remember shutting it down, but it was being very sneaky and it was hiding in the system's background, and that what caused my laptop to crash because I had just shut the lid while it was trying to breed all my resources and causing my whole system to crash. So yeah, that what happened. My laptop, and it's trying to do the same thing now. But yeah, what to do? This is what we are given for big class, and this is what we shall use. Let's upgrade my Zoom. Probably I'll do that. Swap. I don't. Hang on. I can share already. I don't need this. Okay, going to function. So for membership table, when we have an element present in it, we put it as 1. That means element X is a member of set A, for example. Element X is a member of set B, represented by this one. Hang on. Yeah. And then elements X is a member of set C. So then that would be represented by this one here. So when they ask you to check the set equality of A union B intersect C, to say that this is equal to all the elements, or for the set A union B intersect A union C. Now, these two are set identities. We say that when you have it in the form of A union B intersect C, this is the same as taking the A union B, A union C, and then you apply the intersection, right? Just like in algebra, where we say x times a plus b, x times a, x times b, and then you add both of them together. So it's the same way of looking at this here. So when you say that the element in a table construction here like this for the membership table, there must be a certain number of rows. These number of rows are determined by the number of sets that you have here, right? So this is because remember this is all using capital letters since they are in uppercase. So we would assume them to be, or actually they are different sets. So we say this is set A, this is set B, this is set C. If you see in small letters, then it's in the other notation, your set builder notation, where you say X is an element of set A. We can also use A is an element of set A. So you have the small a, lowercase a. So again, don't go and confuse yourself by assuming the wrong one. All upper cases should represent the set itself, and the elements are represented by lower cases. So then we say we construct the table based on the number of elements. How many elements, okay, how many sets there are in the equation is, in this case, there are three sets, A, B, C. So therefore, it is 2 to the power of 3. Or, well, this one we learn later on. There is the way we can prove why is it 2 to the power of n. So n represents the number of sets. So we get 8 rows. 1, 2, 3, 4, 5, 6, 7, 8. So if you only have 2 sets, then it's 2 to the power of 2. That's why you see the basic truth table is always 4 rows, right? True, 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 false, false, true, false, false, right? And then what we do is this first 3 columns, right? This part here represents the individual sets, and the one after that, the subsequent ones we see here represent the individual relationships, right? Or the individual operations within the each side of the equation sign. So why do we have to break it down like this? Is because when we just look at this one here, what do we do is, how do we actually calculate the value? We have to first look at B intersects C, isn't it? And then from B intersects C, I've muted everyone. Why am I still hearing background sound? Anyway, we will first calculate this, and then the result of this, we say A union, whatever it is there. So that's why you notice that here we are doing the individual operation. So first we start with B intersect C. We know that if the element is present in B and it's present in C, therefore this is true, or the element X is a member of B intersect C. And then A union B intersect C. If the element is present in B intersect C and then union A, then we say that it is also present. The element X does exist as a member of this operation. Now we finish on the left hand side. Hence, you must know the difference also where we are looking at what we're looking at. I don't know. And then this represents operation on the left hand side. This represents those on the right hand side. Then we have A union B. So if the element X is present in A and in B, A union B, therefore it exists. And then if the element is present in A union C. So when I say A union C and the element X is a member of A union C, how to know the element exists in there? First, we have to check on your left hand side here. Here represents that the X is present in A, the element X is present in A, in B, and in C. So A union C therefore is 1 because it says the element is present in both. A union B, A union C, we have done these two, so then you only look at your intersection operation for this one here. So we say that if the element X is present in this one and in this one, therefore the intersection, the element X is also present, right? Likewise, for this case, 1 and 1 is present, 1 and 1, right? In this case, if the element is present in here, but not in here, therefore the intersection will yield a false result. That means X is not a member of this case where you only get X as a member of B. If X is in B and not in C, therefore, or even not in A, therefore you will not get it for this operation here. Then likewise for this case here, right? Here we see that when X is only present as a member in set C, of course A union C is true or 1 because if your element is in C but not in A union C still is true, right? You still get X as a member. But now with the intersection, we know that it is not. And then if X is not present in any of the set, therefore this will definitely be 0, right? It will not be in any of the one. So once we have done that, what happens is we have to now compare the left hand side, like I said, to the right hand side. And how do we actually do that? Can anyone would like to guess or would like to attempt on informing us how we do that? We already constructed a table, but we have not completed the proof because we have to, this is just constructing the table to show. That means we have to still prove the distributive law that the left-hand side equation is the same as the right-hand side equation or expression, as we call them. Anyone like to guess? To pull up chat, hang on. I can see the chat. Compare both sides. Yes, that is true. So what we do is now we compare row by row to both sides. So the left hand side, we completed the whole construction of the relationship here for this table here. I'm trying to change the color, the pen color, but it does, no, okay, right? So this represents the left hand side, the completion for the proof on the left hand side, and this is the completion for our right hand side. And then you just compare row by row. So 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 0. Now, since they are exactly the same value for every single row, therefore, they are the same. Because at the end of the day is we're trying to show that the value on the left hand side is equivalent to the right hand side. And these are the values. That means X is present as a member of that expression. Therefore, it will yield that value, whatever X is eventually. If X are, let's say, odd numbers, then you're only going to get your answers all as odd numbers. If you say that X are even numbers, then eventually you're only going to get all those even numbers as a value. So, you understand that? Oh, anyway, this is me having to go through very quickly because the bulk, the main, like I said, the main focus also for proving how you get the rows, the number of rows, and doing the Z proving and the equivalences, the equality is actually done in logic. So here is just to quickly say, just to know how to do membership table, we construct it by relationship to say that X is present in such and such expression, and then we can just identify the zeros and ones. Now, another quicker way to do this would then be by using your Venn diagram, because when you draw and construct your Venn diagram, you are able to then see how we can then we can visualize the membership of this expression, right? So let's say we do one quickly for that one. Now remember the equation was A union B intersect C, right? Is meant to be same or equivalent for A union B intersect A union C, right? So if we were to draw the Venn diagram, now the Venn diagram also has the same relationship or the characteristics as what we saw in the truth table or the membership table. Now we have three sets. So just to recap on how to draw Venn diagram, in case you do not know, go and read up on it. You don't have to choose this level. Now we say that this is set A, this is set B, this is set C, right? Use the shapes. Doesn't have to be this ugly. Now we have a Venn diagram with your universal set outside, right? And you have the three sets and the different kind of relationships that you can find in them. And these relationships are represented by the compartments or what we call as the components in the Venn diagram. So what are the components? Say that this region exclusively refers to elements only found in A, but not found in B or C. Likewise, you can say that this compartment here represents all the elements that you can only find solely or exclusively in B, right? And so on and so forth. So we know the rest. Everyone has done this before. This one in the middle here represents all elements that is found in A, in B, and in. So this is your relationship for A intersect B intersect. Oh yeah, why is that? A intersect B intersect C, right? That's the middle one. Likewise, these would then say or be represented by A union B intersect complement C. That means what you find in, no, you can't say complement. What you find in A in B but not in C. So this A intersect B, the set difference of A intersect B minus C, right? Or what is not present in C can also be A intersect, not in, should be intersect, yes. A intersect B intersect the complement of C. Yeah, it's the same thing, right? Likewise for the rest. So one thing I want, the thing that I wanted to also highlight here is that the number of components are how many? We have this compartment. So this is one, this is two, This is 3, this is 4, this is 5, this is 6. Did I miss out anything? 1, and then this one is 6. This is 7. And finally, outside of those 3 sets, because we have a universal set, is your number 8, which is represented by A union B union C, the complement of that. Complement of all the A union B union C would represent the component of here, right? So you see there are 8 different components. When you look at your membership table, it is also 8 rows represented by those different components. Yeah. So when you say that X is present in set A and it's also present in set B, then what happens? Set A and set B is actually all this, right? There are 1, 2, 3, 4, 5, 6. So 6 rows in your membership table should have it being true. And the other 2 would then be false, right? So that is an example. Where the other 2 is compartment number 3 and number 8, where it is false. So when you go back and refer to your membership table, like for the examples, because I can't show this screen, I cannot swap. It will just be erased immediately once I escape from that. So then you see that if you do not know how to do your membership table, or you want to quickly do it and to be sure that it's correct, you draw the Venn diagram, and then for each row that you've already constructed, all those 8 rows, it's fixed. It's 1, 1, 1, 1, 1, 0, 1, 0, 1, right? This combination of right, the combination that we see there looks like so high on my screen, right? The combination that we see here, they are basically fixed. 1, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, and 0, 0, 0. This is fixed. So this one you memorize it. You have to memorize it. In exams, when I see students trying to construct this table, I get some giving me 5 rows, 6 rows, 7 rows because they can't remember how many rows to start with. Always remember, if there are 3 sets, it's 2 to the power of 3, so there should be 8 rows. If the question has only 2 sets, it should be 2 to the power of 2, therefore we have 4 rows. And then you only have to remember either 2 rows, 4 rows, or 8 rows. We don't ask you to do 16. The next one is what? 2 to the power of 4, 16. We don't do 16 because it's too complex. It'll take a lot of time, right? So remember that one? That sequence 111, 110, 101, 100, 011, 010, 001, and finally all zeros. How to know here is basically saying that X is present in all, followed by X is not present in one set, which is not present in C. And now X is not present in one set, so now X is not present in set B. Just for it to look nice, the next one actually occurs here, where we say X is not present in one set, and that is not in A, but is present in B and C. Then once you're done for 2, then you already reduce 1. Now you're going to reduce 2 sets. So you say that X is not present in 2 sets, which are B and C. Then the combination would be X is not present in A or C, and X is not present in A or B. And finally, the last one combination you can get is X is not present at all in all the 3 sets. So that's how we determine what to put inside here, right? Any question? No question, then we can move on to the next one. So functions. So we finished on sets already. So in functions, we should know, or just to recap, function is basically just saying that we have this relationship between sets, right? Those relationships that we already seen in set, right? As in those expressions of A intersect B, complement C, and all that. Those are actually doing operation, right? But to further extend function, we say that a function f from two sets is always, you can only look at a function between two sets, right? When we say the function f from A to B is an assignment of each element of A to exactly one element of B, right? So that is denoted by this one here. F maps from set A to set B. But when we're looking at value-wise, that means the individual elements, then we use that function. Now we bring in a calculus or an algebra form here to say that FA, whatever element A, it will give you the value B. That value is just basically the element in set B. So we say that it is a unique element of B assigned by the function f to element A. Now, because we say that it is a unique element of B assigned to A, means that there can only be one value of B for every element in A. But when we look at this side here, right, assuming that this is the function f that maps from set A to set B. Oh, is there a question? Somebody want to ask a question? You can interrupt me, but I didn't hear any. I didn't hear any question. All I heard is like a partial sound. All right, in chat. Mm, there's so many. I need to set up the Q&A section so then you can just ask question in that part. You need to scroll down. Is it okay to just stick with one method? I mean, do exam later to use both? There's only one method to use, which is essentially just basically whatever the question requires you to do. The questions are quite specific in terms of what you can use to prove set identity. It allows you to use set identities to prove the relationship where left equals right. Then you have to use the set identity, right? Use the laws. If the question specifically states you must use the membership table, then you must use membership table, because if you use any other method, even drawing Venn diagram, it is considered as zero, even though your answer is correct, but you didn't answer the question properly, right? In the exams, my questions are specific. I will never give a question where it's general and ask you to just solve left equals right. Right. The same thing for logic. In logic, I will tell you specifically either to use the truth table to solve that logical equivalences, or you have to use the uh, equivalence law to basically prove it. So do note that, because in cases where I see students unable to answer the question because they didn't do enough exercises on equivalences, they just try to give me a truth table. So you just wasted your time. Rather, you spend more time doing another question than not answer the question correctly, right? Then give, because to construct a table and then determine the values in each individual cell still take time, and you know that you cannot answer the question, don't bother putting that in. We will not even give it a single mark, not even 0.5 marks, sorry. We just give it straight zero. So That is for that. Any question so far? All right then.
Hello, Mr. Tarin. Can you hear
Yes.
me?
Yes, I can hear
I'm
you.
Virasri here, or you can call me V. I wonder how mathematic examination will be taken place. Like, is it like ABCD, or is it like have to solve it in a subjective manner?
All right. Well, typically, for our exams, we have different formats for it. For first year subjects, normally it's a combination of MCQ, multiple choice questions. It can also be what we call as short structured questions. That means you just give a single value, or because we don't need to show the working of it. Well, you put in your working, but no marks, not a much marks for it. And then we have those long questions where they are divided into different sub questions, like part A, part B, part C. So that means that you have to give a full working for it. So for our discrete mathematics course, we use both MCQ and what we call as short structured questions. So short structured questions still have some form of working, because it's not short questions only just to give a single answer. You have to give the working. So once you do the exam questions, always refer to the marks allocated. When we set the questions, we indicate the value for that question. So the exam, let's say, is 100 marks. For question number one, there is 20 marks, and then question one has subsections A, B, C, right? So A is 10 marks, B is 5, C is 5, for example. So those marks will indicate how much working, how much solution, lines of solutions needed to get the answer. So in a way, it tells you whether there is a lot to write for that question, or there is very little. So, sometimes I see question is 5 marks, but students give me one long page of solution. So it's a waste of time, honestly, because when you are rushing for an exam like discrete mathematics, there's only 3 hours for the final exam. So you do not want to waste time doing something that you know you cannot answer, but you've written so much that you can't have enough time to do other questions. So now, since you're doing online exam, it's changed a lot. It changed drastically in how we implement our exams. Previously, I didn't have any MCQ. It was just purely short structured and long questions. But now we have no choice. We have to put in MCQ, or else I'm just going to get the same answer from everyone. MCQ allows us to have a huge database of questions, and then randomly you assign the question to answer. So not all students will get the same questions and the same answers. All right. Hope that answers your question. Anything else before we move on to function?
No, sir.
No, all right. So I think we can take a short break. It's already 5. I do need a short break. We take 5 minutes break, and then we continue with function. Oh, I just noticed something. You can't see. Am I not sharing the screen?
You are, sir.
Yeah, sharing, isn't it? But I can't pause it. Why you don't allow me to pause? Hmm. Strange. But yeah, 5 minutes break. Lor.
Sir, I think you are muted, sir.
Okay, thank you. Sorry, I forgot to unmute myself. Sorry about that. Now, so just to recap, one element in A can only uniquely be assigned to one element in B that you see here, right? So it means that when you look from the point of view of set A, each element has only one friend in B. But when we look from the point of view of set B, then we can see that each element can have more than one friend coming from A, right? So on this side, which is set A, only one arrow going out from every element or every member. B doesn't have an arrow going out. B only receives whatever A is giving it. And it can have more than one. Not exclusively, only one element in A is being mapped to B. So, but there's specific terms for it, right? So there are specific terminologies, so we go through it to represent the different properties of a set. All elements, all members in set A are known as pre-images, and what you find in set B are known as images. Right? Then we have this arrow that basically shows the function represented by that f. Fa, that means A is an element that would have its value, and that value would point to a certain value you find in set B. The value is just basically the element that is existing in that set, right? What we call as domain is basically all those elements that we find in A. Those elements we find in A are known as pre-images. The whole list of them would represent the domain for it. And in set B, they are known as your codomain. The codomain is essentially all the elements you find. That means all elements. I didn't specifically have to use the term elements. Now, what happened is that not all the elements in B would be an image. So when an element in set B is assigned a pre-image, it becomes an image, and the list of values or the list of elements which are images would then denote what we call as the range. So the range is all the images coming from A pointing into set B. So that means you can have additional elements in set B that are not being assigned a pre-image. But codomain refers to all this. What are those images and those which are not an image, right? That's a codomain. Range only refers to those which are being assigned as images. So you should know the distinction of both, right? So two functions are equal when they have the same domain, the same codomain, and maps each element of the domain to the same element of the codomain. So that means we don't usually do function equality, but just that because they are sets, therefore they would be the same extension of the concept we saw earlier on, where set B are a specific number of elements. So here that B has to be the same. You have 10 elements, set C also has 10 elements, so you want to show that A maps to B the same as A maps to C, they have to have the same full characteristics, right? So when we represent functions, we can either write them using a formula, right? So remember, when we use a formula, like for example, this one here, we are doing discrete math, so most of the questions, commonly, they would have to be integers, round integers. We don't use real numbers when we are representing and we are applying those values. Some cases, you'll see that, we may use a real number, but normally we use integers, right? You can also write it in a computer program, or you just have to define it Because remember, back in set, we are able to just represent it with relationship symbols, operation symbols, or we just define it, we state set A maps to set B, where A are all positive integers and B are all positive integers greater than 100. Then it basically gives you an explicit representation of set, and the same thing that you can apply for representing functions, right? So you can do a quick one here just to see how the different properties of a function. So when we say fa, it's just saying like what the pre-image A is pointing to. Pre-image A points to image B, right? What is the image of D? So we know D is a pre-image, therefore its image will be in set B, and it is Z as well. What is the domain of F? Now, here, because the domain, the set A was not given a set builder notation to represent it, or an explicit statement. So the only way to represent the domain is to list out, to say it's set A, or you can list out the elements in it. In this case, there are elements A, B, C, D, so you just put there as the other way to represent it if you want to make it a bit different than just saying it's set A. Hey, can you, oh yeah, to annotate. So the other way you can represent it, when they ask you what's the domain, then you just say that the domain is represented by element A, element B, element C, element D, right? Like this. So your codomain is, what's a codomain? So in this case, because your codomain represents all your elements in B, so you can just set it as E as well, isn't it? Or to say that it is the elements X, Y, Z. Why I'm showing you two different ways, because if they ask you what's the range, then you know the range is only X, Y. So then there are instances where instead of just saying A, B, you have to list out the elements. So when you always use, for example, this way of listing out the answer, then you won't confuse yourself later on when you need to answer a question and, oh no, I forgot what's the range. Usually I only remember I just have to say set A, set B. So what's the difference between your range or codomain? Right? So to just not confuse yourself. So remember there are two ways of doing it. So it is still possible for you to just answer the question just by giving the elements. Okay? So the pre-image is, oh sorry, that's it for the pre-image of, wrong question. I think, I didn't see the question properly. So it's actually asking for pre-image of Y. So Y only has B. The pre-image of Z, then there are three pre-images, A, C, D. So you see again, you only list it out as elements. So if F maps from A to B, S is a subset of A, then we know that that subset function is basically all, so you say that the function for S is the same as the function for that subset of elements S, such that S are elements of subset S. So if you have A, B, C, D, you have X, Y, Z, again the same function. What are the images for A, B, and C? Or we say FA, FB, FC. This is just a fraction of the original set A. We know it's Y and Z. And what is the images for C and D? they are the same, which is Z. Now, one more thing you have to remember, your domain, the list of elements in your domain, all of those elements must have a value in B. That means they must assign to a image in B, every single element in A. But for B, not all the elements need to have a pre-image. So that is why you have the codomain and range, because there are instances where your codomain is not the same as your range. That means there are some elements in B which are not being mapped or being assigned. Understand? So to further look into the different characteristics of functions, the first one is what we call as injective, right? Injective property is said to be a function that is one-to-one. And this occurs when we say the value of fa is equals to fb and implies that a equals to b for all a and b in the domain of f. Right? So the domain of f is all these elements a, b, c, d. Right? Your codomain are x, y, u, v, all these elements. Yes, is there a question? Question, or somebody accidentally unmuted themselves? So when we say that when we say that why is not Webex muting everyone? I've already disabled all forms of trying to talk or switch on your mic, and I'm still hearing background noise. I wouldn't know because I'm still hearing noise. It's not from my computer. It's, I think, some animal in the background, some table knocking, and all that. So I already muted everyone permanently, but I'm still getting sound. I do not know why is that going on, unless there's a lag in the network. So anyway, moving on. So injection, and when we say that FA equals FB, what it means is that A must be equals to B. What do you mean by A equals to B? And when you see these two, when you see this whole expression here, when you say F equals to FB, A equals to B, or in some other form, we say that X equals to Y, where X is not equals to Y, right? Or we say that Fx equals to Fy, where X is equals to Y. It means that they are the same element or the same value, right? And it implies that that is only a one-to-one kind of relationship. It represents a unique value. A unique value is said to be, if I were to have one random value, A, right? FA would give me some kind of, let's say, X. And I have another random value, B, and that would give me Y. So what happens when we say FA equals FB is that the value X is the same as value of Y. Coincidence, right? Because we've seen that A maps to Z. These are all single ones, right? Some cases earlier on we saw what A maps to Z, B maps to Z. So happen, right? A can be Z, B can also be to Z, and then Z equals Z. But to give it that uniqueness, then we say that that can only happen if A equals to B, and A equals to B means what? the value here is only A. There is no such thing as some other value. So that would imply that there is a uniqueness in the property. So the uniqueness of the relationship here is what we call as injection. A one-to-one relationship. Only one unique value of A can basically map to one value of B. Right? So normally we say that the relationship is many to one. A many to one is seen in the case of the earlier slide where you can have multiple pre-images pointing to one image. Right? Injection says that you can only have it as one to one. Can it be many to many? Oh, you can't answer. I muted everyone. If you're trying to speak, you want to can put it in the chat. Can it be many to many? No. And the reason is, why do you all think it's you can't have many to many relationship? A many to many relationship is going against the basic rule for function, that one pre-image can only uniquely have one image. A many to many means that one value in set A can have multiple values in set B, and there's no such thing as in for function mapping. You can't say fx equals to one value of A and then you can have another fx, they have another value B. No such thing, right? You say x plus y equals to z, one value of x, one value, specific value for y. When you add them up, will only give you one specific value for z. Unless you're going to use the square root, then probably you can get two values, but that's out of the scope here, right? So the next property that we can look at are known or is known as that. If only you can see what I'm actually doing, then you can actually understand my frustration. If you see drawings and everything, I'm not even selecting anything from the annotation, and yet it's just doing whatever it wants. So surjection is the next property, and that is saying that it is an onto or surjective instance if and only if every element B in your set B, there's an element A in set A with FA equals to B. So a function f is called surjection if it is onto, or it's surjective, right? So what does that mean? It means that your codomain is the same as your range. So there is no element in B that doesn't have a pre-image, right? Every element in B must be assigned by an element in A. Now in this case, right, you notice that it can have that many to one relationship. Doesn't need to be individual injection, right? The injective state and the surjective state. What we will create is then the third property and the most important one actually, which is to say that it is only one-to-one assignment, and at the same time it has to be all images, all elements in B being an image from A. So onto and one-to-one would then create this bijection. And why bijection is important? Because this correspondence, what we call as a one-to-one correspondence, and at the same time, remember, there is no element in B that is not an image, would allow us to have what is called an inverse function. So you can only invert a function if it is one-to-one and as well as onto. Because if you're trying to look, you're trying to invert a function, and if it is in the form of many to one, then it violates the rule for function. Because an inverse function is basically now from, instead of saying function A maps to B, when you invert it, it basically becomes the case of you mapping B to A. So when you're going to do it from B to A, each of the element here now, if it's a many to one for A, now you violate it because you're trying to say that one pre-image has multiple images. So you cannot invert it. When it is in the form of onto with the onto property, then again we do not violate the second rule for function, where you say that every element in set A must be mapped to set B. So if your codomain is not the same as your range, then when you invert it, you would have additional, early on they were not images, isn't it? So now when you're trying to invert the function, you get the case of these elements which are not going to have any assignment. And then again, it violates the function rule. So to invert a function, it has to be both injective as well as surjective. Now that summarizes this whole thing here and how you represent it. So just going back to this one here though. So showing f is one-to-one or onto, this is just a general condition that you can apply when wanting to answer questions. It asks you like, if you are given set A are all integers, set B are all real numbers, right? And the function is defined as the square root of x, where x is all positive integers. Then is it possible that you get your assignment as real numbers? If you say that set A are all integers, set B are all integers, then not all square root of integers would give you the result back as integers. So then you have a case of codomain is not the same as your range. So then that is how we can able to identify it. So to show that f is injective, we say that they must be the same value, and at the same time we say that these two values of x and y, they are what? With x not equals to y, then x equals to y. What does it mean? An arbitrary. So the word here is arbitrary. I used random earlier on. So that means any random, or you just pluck some value, assign it to x. You pluck some value and assign it to y. As long as x and y are in A, and if they have the same value, it only means that x and y must be the same and that is unique. If x and y are not the same, that means you're saying two different values or two different pre-images. This means two different pre-images. This one means the same, identical pre-image. That's about it. And to show f is surjective, we just consider the an arbitrary element y in B and find an element x in A such that fx equals to y. So now we have to first determine that all the elements in B are images. So the example where I say the square root of an integer, you can just look at just the first few sequence of integers. Right, let's say 0, 1, 2, 3, 4, 5. We know that 1 is square root of 1. 2, there is no such uh, integer that if you, so you can actually, 2 would be 4, right? 3 is 9, and then so on and so forth. So you notice that actually the codomain is the same as the range in that instance. So I mean, It should be the same because it's square root. I'm not saying square. So that is how we generally look at finding onto. So this one is, let's look at an example. If f is a function from this set, so here instead of giving a label a and b, they represented by the elements in it. So we have set A, A, B, C, D, and set B, 1, 2, 3. And their assignment are already given. The assignments f a equals to 3, f b equals to 2, f c equals to 1, f d equals to 3. Now, is this an onto function? Now, go back and remember onto means all the elements in B must be assigned. So you see, in this case, the values are 1, 2, 3, which is the whole list of elements in B. So this is an onto function, right? Is the function fx equals x squared from set of integers onto? So here the solution, of course, we know is no. F is not onto because there is no integer x such that x squared equals to -1, right? The other way to do it, or to try to attempt questions like this, would be what? You sketch a graph of it. So if you just sketch the graph, what you get is you have your rest. If you try to draw the graph, you will get x and y axis, right? And here is fx equals to x squared. So we know that the minimum value is the minimum value is 0. So you get a graph, a U-shaped graph. If you try to draw the graph, think from x equals to 0 or y equals to 0. So in this case, we know that the codomain is not the same as the range, which is represented by your y-axis. So your y-axis represent your codomain, right? Whatever the values under the area of the curve or line or everything would then represent, sorry, am I saying, am I doing it correctly? It's under the curve, not above the curve. That's above the curve. Oops, I did the whole thing. So, and we have our graph, the fx graph. So we have the area under the curve would represent your code, your range of values. So this is your range of values here. And notice that it doesn't span all the values for your y-axis, because y is what? We say that they are set of integers. So your integer will be 0 and above until infinity. And we have going down this way for negative infinity. So it never goes, or the curve doesn't extend to this side of the graph or the x-axis. So therefore, it is not a case of onto. So if you to draw a straight line, let's say y equals x plus 2. So you have a line like this. Then the area below the curve or the line, sorry, would be all these values because this is represented by what is value x? What is the value of y at point x? What is the value of this x2 and so on and so forth. So this is the area here, and they all would represent the whole domain, codomain, sorry, of y. So then it is onto, because it extends to from negative infinity all the way to infinity, right? So that is using a graph solution for that question. Oh, never say question. control this stuff. I don't know. And what else? The inverse function. So when you have A mapping to B, this is representing all the assignments from A to B. So you notice very quickly using this kind of diagrams, right? It's another way for us to solve questions related to functions. And you can solve them very fast. So we can see that it is 1 to 1. At the same time, it's onto, so it's bijection. And when we want to create the inverse of it, then we just change the direction of the arrow. And we notice now that all elements now in B are three images having one unique assignment in A, right? So if you have a case where there are elements here that cannot be assigned, then we know that it is not it cannot be inverted, right? What else? The other one, it has to be 1 to 1. Or else you're going to get a case of one pre-image pointing to multiple, oops, right? Pointing to multiple values or multiple images. So let f be the function from a, b, c to 1 to 3 such that f equals to 2, fb equals to 3, fc equals to 1. Is f invertible and what's the inverse? So first thing to do when you want to check for inverse, like in this case, you can already see that this all those elements here, the number of elements in both sets are the same. If they are not the same, then automatically you will definitely not find an inverse of it. So you can really claim that it is not invertible, right? And now they are the same number of elements, so we have to move on to check for both properties, whether it's onto as well as 1 to 1. In this case, we can see that FA points to 2, FB points to 3, FC points to 1. So there are no repeats of the value, so therefore that's 1 to 1. Same time, we see that the values are 1, 2, and 3, and they represent all the values in set B, so it is onto. Therefore, it is invertible. And when you invert it, all you say now is F1 equals to C, F2 equals to A, and F3 equals to B. Easy. Now you have a function that maps all integers. This means negative infinity to infinity, right? And you have the equation x plus 1. Is it invertible? Yes, it is invertible. So what is the inverse of it? The correspondence would be the inverse of y equals to y minus 1. You all know, isn't it, how to get the inverse of a function when you're using the equation or the formula? You say, yes, that's good then. But just to recap for those who can't remember quickly, you have a function fx equals to y, right? So what does it say? We say that y equals to certain formula, 2x plus 3. Inverting it means taking all that is on the right hand side and dumping on the left hand side. So now you have x as the reference. So when you dump everything, what you're going to get? You're going to get f minus 1 y equals, are we still using y? Yes. Which is y minus 3 divided by 2. Or you want to go back and put it in its original form, we say that this is the inverse of a function. So we have x equals to y minus 3 over 2, right? Let's quickly show you. So here, you should know what this is going to be. What else? If we have the function mapping from R to R such that fx equals to x squared, so I already proved this using the graph plot. So we know it is not 1 to 1, right? And it's also not on 2 because when we draw the the x square graph, it goes from 0 and above values, right? For your images. So that's on 2. But it's also not 1-to-1 because a negative value of x would assign the same value as a positive value as the positive x. So a positive x and a negative x will yield the same y value. So therefore, it is not invertible because it's not 1-to-1. Then this one here. This to this right. Oh, that's the annotation. The orientation. All right. Composition. What is composition? Composition is just basically you defining a function within a function, right? It's just like thinking of it as multiplication. When you multiply sets, right? Your Cartesian product basically says that what the elements in A, you multiply it to point it to some elements in B. So that is one function, A to B. And then you have another function, B to C. So when you multiply the Cartesian product of two different sets operations, would yield something from A to B, from B to C, so you get it from A to C. So this is what we see here in this diagram. All the elements that are mapped in function G are A to B, right? So that's why you see this is element A and the value you get for GA. And then this is your function F, where it maps all the elements in B. So you have the case of elements B here, and then you're going to get the function that would give you the value for FB, right? So when you compose it, is you're saying you're applying the function GA within F. This is FA lah, or FX, sorry. X here. Okay. So the composition or the compose operation is denoted by the dot, right? So F dot G or F compose G, always remember you have to perform G first and then apply it to Fx. So Gx has to be done first, followed by Fx. So that's why you see Gx is here, not Fx. Common mistake students make when they see this, they go and draw it like this, but they call this one as Fx instead of calling it Gx. And then you cannot answer because you see that suddenly everything stops here. That occurs when they are not using the same set. A, B, C, D. B is 1, 2, 3, 4. So then when you do the assignment wrongly, you notice that you cannot map it because this is not the middle set that is common for both function, right? You're going to get it as instead of A, B, C, and then 1, 2, 3, and you're going to get it differently, right? So those are when there are different sets up. So always remember, do Gx first and then followed by Fx. I'm still getting students giving me answers as Fx first and then Gx. I do not know why. Something you learn, I remember form 3, form 4, right? So this represents your F compose G. You can also invert this if you want to, but you'll just make our diagram here so complicated, so it's not showing you how to do it, right? So Samia's question, let me see. Now raise your hand, then you put in the chat. I don't want to constantly mute and Everybody. All right. Oh, you've never done this before? Probably it's not in your basic maths that you've done. Probably it's in the ad maths. I can't remember. Then to graphically represent a composition of function, and why I say that sometimes if you wrongly assign and do F first and then G, you will get it. You will not be able to see the flow of it. A to Y, Y to J. So the composition result would be A points only to J. B to W, W to H. So you get BH. Then you can get C, I. And then D, H. Right? Try to do the opposite and C, G compose F. You get the same answer. Now this is using the graphical form. The other form is to look at formulas and then assign the formula in respect to the other one. So when we say fx is equals to x squared, gx equals to 2x plus 1, then what is this one here? That is g compose f. Is it, or f compose g? That is your f compose g. Because we do the g first and then we assign it to f. G fx is basically saying g compose f. We take the function for fx and we apply it into the function of g. Right? So straightforward again, we just take for the first case, we take the 2x plus 1 and then we plug it into x squared. That's why you get 2x plus 1 squared. Whereas the second case, we just take the x squared and we plug it into gx in here. So we get only 2x squared plus 1. Easy. One question here. Let g be the function from set ABC to itself. So when you see the word to itself or onto itself, then it means you're using the same values for the set A and B. So we have GA maps to B, GB maps to C, GC maps to A. Let F be the function given as such. What's the composition of both? So first question is F compose G. So since it is F compose G, we have to first draw the composition. Sorry, the function for it. So this has to be G first, and then followed by F. So then we have F compose G. So what is G? G, A, B, C. We have A, B, C. We know it's onto itself, isn't it? So it's A again, B, and C. So we have the mapping GA equals to B. So we have GA equals to B. And then we have B to C. And we also have C to A. Oops. This is C to M. And then for function F, we see that FA equals, oh, so I forgot to add this one. So here is 1, 2, 3. So FA maps to 3, and then B maps to 2, and C maps to 1. So what's the solution for F compose G? It's A points to B points to 2. So we have A2, and then we have B points to C points to 1. So we have B1. And the final one is C to A to 3. So you got C3. Right? So that is the composition of Fn. So for G compose F, well, you can either recreate the whole diagram or you can just add only one additional set at the back to represent the G compose F. So what is G compose F? G compose F is taking the function of F first and then applying the function on G. So now the case here is what? That's why it is you have to be careful. Here, G says that it has to be A, B, and C. But in this case, it is 1, 2, 3. So there is no A, B, C there, isn't it? So in this case, what we say? Undefined, right? There is no such value for, or there's no such composition G compose F. Understand? So for the first one, we see straightforward. You just draw it. You can get already drew it, right? For the F, the range of values for F 1, 2, 3, they are not part of G because G starts from A, B, C. Okay, the F and G, B. So this in this case, you just have to put one into the other. So that's straightforward. Quickly, F compose G. Remember, we're taking G first, which is 3x plus 2. We plug it into 2x plus 3 to give us 6x plus 7. G compose F is basically saying taking 2x plus 3 and plug it into 3x plus 2. So 6x plus 11. And then there are these two unique functions. They are actually unique to in computer science. When you're doing your programming, your coding, sometimes you would actually apply the floor and ceiling function because you are trying to, for example, do a certain display. You're trying to output your display, and then you want to work with just integers, right? Or you want to print out pages. So these floor and ceiling functions, they are basically they come in handy lah for those instances, right? Like pagination and all that. So the floor function basically says that fx equals to this symbol here. So I normally say that if you look at this, this is like as if your hands are going down. And this is your hands above your head. So this is your lowered hands and this is your raised hands. So when you see a function like this, basically it looks for the integer nearest to it, either below that value x or the integer that is immediately above the value of x. So x here can either be integers, they can be in any form, so they are real numbers generally. It's not stated, but they are real numbers, or else we wouldn't be using them if they're just integers. So how do we find the value? Straightforward. The first one, 3.5. So the nearest integer, which is above 3.5, would then be 4. The floor function for 3.5 would say that the integer just below it is 3, right? Negative value. Now, negative value, you have to be careful. So for negative 1.5, the ceiling is minus 1, and the floor function for negative 1.5 is minus 2. And why is that so? You can just represent your floor and ceiling function using a scale. So you have 0, you have 1, 2, 3. So anything above 0 are all positive integers. Below that are your negative integers. So a floor function for any value that you pick, let's say now I want to look at value, who's already 6, huh? I just quickly finish this one. I want to look at the floor of 1.7, right? And then we have the ceiling of 1.7. So 1.7 is somewhere here, right? Put it outside and it's easier to see. So the ceiling function says that you're going to rise to the next integer. The floor function basically say you are going to you're going to sink to the next integer, right? So floor you go up, ceiling you go up, floor you go down. So you know that then the ceiling of 1.7 is 2, the floor of 1.7 is 1. For a negative number instead, let's say I choose a value here, minus 1.5. So it's the same thing. The ceiling of negative 1.5, you rise up to the next integer, which is minus 1. And the floor function say you're going to go down to the next integer. You're going to sink to the next integer. And then the next integer is minus 2. That is why the question for negative 1.5 has the ceiling as minus 1 and the floor as minus 2. So this is the easiest way to explain it, and yeah, you shouldn't be confused anymore with the ceiling and floor function. Understood? All right, so I think we can stop here. Sorry, 6, so let me see how much more left. Like, finish, I think I must finish. Yeah, so that's how you see it in the floor and ceiling function. I don't know why they use it this way. Such a bad representation of a diagram. You use in the opposite way of rising up and sinking lower, then you can see it actually easier than using this kind of scale. Anyway, same thing lah. These are the floor and ceiling functions for certain numbers. If x is equals to or less than n, and x is lesser than n plus 1, then the floor of x is n, the ceiling of x is n. I don't know what is all this. No point remembering Melissa. Here is what? The negative of, the floor of a negative integer is the same as you find the ceiling of x when it's positive, and then you negate it. Likewise, the ceiling of x, the negative value of x is the same as you first finding x floor value and then you negate it. N is a constant, so x plus n is the same as you just have to look for what is the value of the floor and ceiling function of x, and then you plus with n because n is a constant, right? So this is like in the case of if you generated, the floor and ceiling values for 1, 1.1, 1.2, 1.3, blah, 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 right? And the constant now is, let's say, 10. Then automatically you can find the values for 10.1, 10.2, 10, sorry, plus 10. So this is 1. So 11.1, 11.2, 11.3, 11.4 subsequently, right? It repeats itself as a pattern. So yeah, that actually supposed to end that section. So then we learn about sequences, which are mathematical patterns. What is a sequence? Sequence are a list of number in order, and they appear because there is a pattern mathematically to represent those values. So I think we can stop here. this will take a while. Sequence and summation will take at least a good half an hour or so. So, any question? All are muted, so let me unmute you. Mute on entries. Ready. Thank you very much, class. I'll see you next Thursday. What I'll do is for the sequence and summation, I will record the video lecture for it and then I'll upload it. So then we can start with the new one. Sequence and summation, I think I would rather instead of wasting too much time next week, I can then spend 1 hour lecture, do a 1 hour video lecture on this, so I can slowly explain what I need to explain. All right then. Thank you very much. See you next week. Have a good weekend.
Thank you, sir. Bye
Thank you,
bye.
sir.
Thank
Thank you
you.
very much, sir. Yes, sir.